Okay, I think then we can also start. So once again, welcome, ladies and gentlemen, to our CRM geothermal webinar on unlocking the power of AI in lithium exploration. My name is Katrin Kieling. I'm working at the Helmholtz Center for Geosciences, GFZ, in Potsdam, Germany, and I am the project manager of the CRM geothermal project, which is an Horizon Europe project on raw materials from geothermal fluids, occurrence, enrichment, and extraction. In this project, I have the pleasure to work alongside with a number of outstanding researchers from 20 European and non-European universities, research centers, industry, and geoscience associations. And we are all committed to developing an innovative technology to secure our growing need for raw materials for the energy and the digital transition. In today's webinar, we will explore the application of artificial intelligence tools to the complex geothermal data sets, since geothermal systems bring together geological, chemical, and thermal processes, and those interact in a nonlinear and unpredictable ways. So focusing on the critical raw material lithium, our colleagues from our project partner INLECOM have developed the CRM geothermal lithium estimation AI tool. So now we will have a look at the agenda for today's webinar. We are going to start with a short introduction on CRM geothermal by myself, and then my colleague Costas will introduce you the company INLECOM, handing over then to Stathis, who is introducing the AI tool, and we will have a number of some demo videos so that you can really get an impression of the tool, have a technical discussion, and finally show some commercial exploitation ways. At the end, we will have a question and answer session where you can ask questions. And already now I ask you to put your questions into the Q&A tool, and I will then read out your questions to my colleagues, Costas and Stathis. So a last remark before we start, you have probably noticed the webinar will be recorded, and my colleague Tamas Miklovic from the European Federation of Geologists, who has actually set up this webinar, will publish it then afterwards on YouTube. And with that, I will kick off with the presentation of the project. So CRM geothermal, some facts and the challenge of the project. So we really face the challenge that large amounts of critical raw materials are needed for the energy and the digital transition. And you can see from the figure that alone the transition from combustion cars to electric vehicles will increase the demand for certain raw materials really a lot. And the same is true for the renewable energies. They all need a lot of different critical raw materials. So we really see that Europe needs a resilient and domestic CRM supply chain that reduces imports that are exposed to market and political risks. In the project, we suppose CRM extraction from geothermal fluids, since we have seen that geothermal fluids have the potential to cover really a significant percentage of current and future needs of the European critical raw materials. And it also aligns perfectly with the European Critical Raw Materials Act, where we have the goal of 10% raw materials extraction from the EU and also 40% of EU processing. And in our project, if you click once more, Stasis, then you can also see that we are exactly contributing to those two parts of the Critical Raw Materials Act. Next slide. Yeah, so the concept of our project is to combine the extraction of heat or electricity and the extraction of valuable elements from geothermal fluids. So we will at the same site have both heat and CRM production. The advantages are relatively clear. With this combined extraction, we are maximizing returns on investment, we are avoiding additional land use, and we are also minimizing the environmental impact of mining. So our goal is really here to make mining invisible. In the project, this is a project which answered the Horizon Europe call, innovation for responsible EU sourcing of primary raw materials. And we are working together 20 partners, 19 affiliated entities. You can see all the partners that are contributing to our project here. And we have a project duration of 48 months. So we started in May 2022, and we will finish next year in April. Um, the main activities of the project are that we are first establishing an overview on the potential for raw materials from geothermal fluids. So we have a look at the different fluids and see what their chemical composition is and which raw materials are actually in them. Then we determine the source of selected CRMs, their mobility, their potential for a sustained extraction from the brines, for example, by also having a look at how quickly is a depleted brine recharged again once it travels through the underground back to the production well. We are developing and optimizing innovative extraction technologies for some of the CRMs, and then assessing the environmental, social, and economic viability of the process to foster an ethical sourcing of CRMs. And finally, we are bringing this all together at the demonstration site where we want to demonstrate the technology at the scale of a mini plant. I'm summarizing in the next few slides a few of the highlights. So as I said, we are doing a screening of different geothermal fluids, and we are summarizing it in a fluid atlas. So in this fluid atlas, we are providing the public data on CRMs contained in geothermal fluids. We want to really include all the different CRMs, so kind of the whole periodic table. And this is mainly based on a database from a previous project, from the Reflect project, but then we have added in the current project already a lot of data analysis from fluid sampling and also rock sampling. And actually the AI tool makes use of this database and has trained the tool with this database. We have also the extraction technologies. We actually have 6 different extraction technologies here. I'm highlighting only one of them, the example of oxalic acid mediated lithium biorecovery. So we have investigated what contribution microbes can make to the extraction of lithium. And this is already published in a deliverable. If you scan the QR code, you will directly get to this deliverable. As I've said, we want to demonstrate everything at a pilot site in Cornwall. In Cornwall, we are working together with Cornish Lithium and Geothermal Engineering Limited, but also with Levin Sources, who are a responsible mining consultancy. And yeah, actually the technical testing focuses on the boreholes of Cornish Lithium in United Downs, so really in the very southwest of England. And then I've already mentioned Levin Sources has established guidelines to obtain and maintain a social license to operate. Also, this deliverable is already published, and I invite you to have a look at it. They have really come up with these 7 main principles to respect to obtain and maintain a social license to operate. And this is also a bit of a save the date, because already our next webinar will be on 23rd October, again at 2 o'clock, on this societal engagement and geothermal projects in combination with CRM extraction or CO2 storage, because it's actually a joint webinar between CRM Geothermal and the SEEKS project. And then another save the date, we will also have the CRM Geothermal Conference next year, 25th of February in Offenburg in Germany. So this will be a half-day event prior to the geotherm exhibition. And yeah, you will get first insights on results from the CRM Geothermal project, and also will have the possibility to interact with our researchers and innovators. And I think that's all from my side as a short introduction to the project. I thank you for your attention. And now I will hand over to my colleagues from INLECOM, to Costas Lupos and Stasis Antonio. I will first introduce shortly both of them. So Costas is the R&D director at INLECOM Innovation. He holds a master in business administration from the Hellenic Open University and a master of science in microelectronic systems design from the University of Southampton, as well as a master in electronic and electrical engineering from the University of Manchester. His research interests and activities range mainly in the Internet of Things or ICT systems, cybersecurity, sensors and systems for structural health monitoring of infrastructure, robotics, water demand management, wireless sensor networks, and application-specific embedded systems. He is now working at INLECOM and has been substantial in defining the focus of the AI tool for our CRM geothermal project. And then our second speaker is Dr. Stasis Antonio. He's a head of AI research, also at INLECOM Innovation, and has led multiple projects in the field of AI and mathematical modeling. He holds a PhD in mathematical modeling from the National Technical University of Athens and a Master of Science in Machine Learning from the École Polytechnique de France. He has worked and led data scientists and statisticians in various companies and has extensive experience in management and implementation of end-to-end machine learning pipelines that align with business KPIs and EU trustworthiness standards. And with that, I have the pleasure to hand over to Kostas first, who will introduce you to INLECOM.
Thanks a lot, Katrine. Thank you so much. Thanks for the introduction. Very well said and very well introduced. As you can see, CRM geothermal is expected to bring a huge innovation in the exploration aspects, and this is also very much aligned with our innovation strategy in INLECOM Innovation. So INLECOM, a few words about INLECOM is an SME in Greece, in Athens. We have a very strong participation in research projects where we apply different technologies into industrial prototypes. We have a very strong R&D participation in Horizon projects. We have something like 25 running right now, and of course the related proposal writing and networking sections. On the right, you can see some of our technical competencies, starting from the AI, machine learning, NLP, digital twins, computer vision, everything that has to do with predictive modeling, decision support, simulations, this part of technologies. And we have also another team on distributed ledgers, smart contracts and encryptions for digital identities, smart contracts, and of course, cybersecurity and identity management. And we also undertake responsibilities on ICT platform development, data processing, big data, system integration, data fusion, things like this. Next slide, please. A lot of applications where we apply our technologies include, of course, applied ICT, Internet of Things, transport and logistics, which is a very long history of the company, including supply chain and food, circular economy, security, energy, but also green building and smart cities. Regarding different materials and technologies, but also health and manufacturing as well. On the right, you can see an alignment with European Commission clusters on health, culture, security, space, climate, energy, and of course food, bioeconomy, etc. Okay, I think I will pass the floor to Stathis, our head of AI, to introduce more the AI tool and talk in more specifics. Thank you.
Thank you very much, Kostas. Thank you, Katrine. So I will guide you through the tool, explaining some high level at first, and then diving into some more technical details. So what was the goal of the AI tool? I'm going to start by that. In plain words, it was to fuse geothermal and data science in order to be able to decipher all this interplay between elemental feature, fluid characteristic, and lithium concentration. And that, if you translate that to something, to a task to give to a data science, that becomes to develop a tool that delivers accurate estimation of lithium and is interpretable. So that was our goal. How did we do that? The steps, the broad steps are shown here. First, we had to define the scope we did a lot of searching on which areas can ML provide insights that are really valuable to geoscientists. Then we selected the data set, just like Catherine mentioned. We were lucky on that side because there was already good data available, not the case in many data science projects. Then we spent some time choosing the feature, mainly based on the data availability. Then a lot of time on data engineering. We made a new methodology for detecting outliers, new in a sense that we didn't use classical Z-score or other things. We also did some data augmentation in order to have an unbiased model. Then we trained model and validated, just like all machine learning projects. Then we added the explainability layer. We decided to go with Shapley values in order to add explainability. And then we added some more functionality to explore additional relationships between features themselves and between the output of the tool and the geographical patterns of the data. And afterwards, we developed the tool. Initial version was using Jupyter Notebook, and then the final version was a web-based tool with a friendly user interface where we use Gradio, which is a very nice tool for passing from Jupyter Notebook to a web-based tool. So I'm going to show now two videos that show you the tool, and then we're going to get back from some more technical details. So enjoy the screening, and for the next 5 minutes will be for the tool, for the video.
Welcome to the Lithium Estimation AI Tool. On the landing page of the tool, an overview is provided that outlines the scope of the tool, the machine learning technologies employed, and a brief description of its functionalities. This part constitutes one of the two central functionalities of the CRM AI tool. Primarily, the model provides an estimation of the lithium concentration, and the second facet of the output serves to offer transparency and a comprehensive understanding of how the model arrives at its predictions. Initially, the user can select the type of the model they wish to use. The default model is a decision tree trained on features in milligram per liter in the liquid phase, specifically calcium, chlorine, potassium, magnesium, and sodium. Alternatively, users have the option to create a custom model, referred to as the custom model, by selecting additional features. The decision tree model will then be updated to include the selected features in its predictions. Once the model selection is confirmed, two primary plots are presented: the measured lithium vs predicted lithium plot, which also displays the performance metrics of the model, and the Bisworm-Shapley plot. As example, we have selected the default features and a sample taken in Germany, which is part of the test dataset. In this sample, the model's estimated lithium concentration is 179 mg per liter, while the measured value is recorded as 176. By examining the water-flow-Shapley explainable AI plot, 17.25 mg per liter is the average predicted lithium across all 516 samples in the test dataset, and 179 mg per liter is the predicted lithium for the specific sample. Also, the plot tells us how each feature has contributed to this prediction. As we can see, potassium appears to have the highest impact on the specific sample and has increased the predicted lithium value by 116 mg per liter compared to the average predicted lithium. Similarly, sodium, calcium, and chlorine have increased the estimated value. Conversely, magnesium has decreased the prediction by 0.15 mg per liter. It is observed that the algorithm reached a decision after crossing 5 nodes, concluding at the final leaf that contains one sample from the same well, and as seen on the left, with mean lithium concentration 166 mg per liter, including training dataset. As the decision tree step slider is moved backward, changes are observed in the plots and the range of feature values expands. On the left, a list of wells is provided, for which any or all samples correspond to the selected decision tree node along with their mean lithium values. For instance, at node 3, 8 samples are found with an average lithium concentration of 200.9 mg per liter, which are not only feature-wise similar, but also geographically close. As the slider is moved further, it can be seen that the wells with a wide range of feature values are included as expected. Additionally, a bespoke methodology tailored for outlier detection was crafted, ensuring a novel approach to discerning between genuine outliers and instances of inherent variance for each well. If only one sample stands out, it is flagged as an outlier. If there was at least one matching pair within the well, it was left in the dataset and considered as indicative of high variance within the well, possibly due to different measurements at different timestamps. Consequently, the test samples in the CRM dataset have been processed to ensure the absence of outliers. In the previous example, the final decision of the decision tree was based on a sample from the same well. If the sample did not appear in the final decision step, it would be necessary to step the slider backward to check if it was included in the previous steps. Decision trees select their paths randomly, and sometimes a very similar sample in terms of feature values can be split just before the final node, causing it not to be considered in the final node. This is crucial to avoid drawing incorrect conclusions about whether a sample is an outlier or not. In the case of a newly manually inputted sample, the user can assess its potential as an outlier. As an example, we consider a sample taken from a well in Denmark from the test dataset with the feature values as shown here. This serves as a reference to illustrate the tool's capability to incorporate tolerances of new sample measurements from the same well while identifying outliers. Initially slightly different values were added based on the existing tolerances found within sample measurements in the CRM dataset. The tool correctly predicted the lithium concentration, estimating 10 mg per liter, where the reference well has a mean lithium concentration of 9.6 mg per liter, incorporating a sample from the same well in the final decision tree node. Therefore, this theoretical new sample is not considered an outlier for the corresponding well. Conversely, by keeping the rest of the input the same but decreasing the magnesium concentration to half, the tool failed to predict the lithium concentration accurately. Even though the prediction was close to the range, the tool did not match the sample with Denmark's, even when stepping the slider backward a few steps. Instead, the matching samples were from wells not geographically close to the reference sample. Therefore, this theoretical sample could be considered as a potential outlier.
Right. A lot to unpack there. I hope it will become clearer with the next video and the details that I will tell later. We do want it to show a maximum of the capability of the tool, but bear with me and we'll dive into the details in a second. So here is the second video.
In the second major component of the tool, the primary objective is to expose the interplay between lithium and the input features within specified ranges of those features, particular geographical regions or specific reservoir types. This part of the tool requires the user to start by selecting features. The default features are potassium, magnesium, sodium, chlorine, and calcium, while the custom optional features include strontium, boron, outflow temperature, and electrical conductivity. Once the user has selected and confirmed the desired features, a newly made model is instantly trained on the entire range of selected features. In this example, the default features are confirmed. Instantly, the model performance plot and the explainable AI Beeswax-Shapley plot are displayed, along with well information, including the number of wells, the number of samples, and the mean lithium concentration of all samples. Additionally, sliders for the lower and upper limits are provided, allowing users to adjust not only the input features but also the range of lithium, as well as the latitude and longitude of the samples on the map, and also finally filter by the reservoir type. In the middle section, scatter plots display each feature from the test set against lithium concentration. A map is also included depicting the locations of the wells that correspond to the test samples with the color bar indicating lithium concentration. We begin by selecting only the high enthalpy type. By narrowing the latitude lower limit slider, Martinique and Guadeloupe are excluded as they are not geographically located in Europe. It is observed that the model performance is exceptionally good. At first glance, one sample appears to deviate significantly from the others, shown on the map in black, with the lithium concentration around 300 mg per liter, compared to all the other samples which are below 100. This particular well had only one sample, therefore it is now excluded from the analysis by limiting the lithium values to a maximum of 330 mg per liter. Following this adjustment, two samples now appear to deviate From the BIS1 supply plot, it is evident that both chlorine and sodium significantly increase the predicted lithium concentration when they are at high and very high values. The samples were checked correspond to 2 wells in Greece. They were excluded from the current analysis by narrowing the chlorine concentration to a maximum of 40,000 mg per litre. The distributions now become particularly interesting as sodium, chlorine, and calcium exhibit similar trends, with their values spread nearly uniformly along the x-axis, and potentially clusters begin to emerge. Magnesium and potassium also display similar patterns, although different from the other 3 elements. The vast majority of the values are concentrated in the lower band of the x-axis, clearly forming 2 clusters. However, there are a few samples with lithium concentration close to 0 that have potassium levels exceeding 40,000 mg per litre and magnesium levels over 1,250. Since these extreme values for magnesium and potassium do not belong to the same samples, the samples with high potassium levels were first examined. These samples were found to correspond to Sardinia and Italy. Despite the exceptionally high potassium levels, all the other elements, including lithium, were observed to be in the lower range. By narrowing the potassium concentration to a maximum of 40,000 mg per litre, these values were excluded. Potassium appears to be the most important element, with its low, middle, and few high values having a moderately distinctive contribution towards the prediction of low lithium concentration. However, high and very high potassium levels hold high Shapley values, significantly contributing to the high predicted lithium values. This is also evident in the scatter plot of potassium, where a cluster in the higher range is apparent. Returning to BIS1 plot, a small number of high potassium values, colored reddish, appear to have a moderate negative contribution, which is visible below in the cluster in the scatter plot. The same cluster is also observed in calcium, chlorine, and unsurprisingly sodium, which is ranked 3rd in feature importance. It is important to know that even though calcium and chlorine exhibit almost identical response patterns to sodium, they are ranked last in feature importance. This most likely occurs because the decision tree splits are made based on sodium, causing the other 2 elements which exhibit similar response patterns, possible collinearity to sodium, to have a moderate impact on lithium predictions. Magnesium ranks 2nd in feature importance. High feature values exhibit a strong negative contribution, whereas low feature values demonstrate a strongly positive contribution. These trends are clearly evident in the scatter plot, and the previously mentioned cluster of lithium concentration above 15 mg per litre corresponds to low magnesium values. Next, the sliders are narrowed to extract the cluster of high lithium, achieved by limiting the sodium lower limit to 15,000 mg per litre, where the distinction is more evident. This cluster corresponds to the 3 wells of Tuzla geothermal region in Turkey. The key observation is that this geothermal region deviates from other high enthalpy regions, with potassium as the most significant deviating feature, alongside with salinity and calcium levels, but with low magnesium values as shown in the previous step. This alignment with the literature not only validates the analytical approach employed, but also enhances the credibility of the model's explainable capabilities.
So you just heard Kelly Sava, who made a very good job of telling exemplify what the tool can do. So Kelly Sava, together with Nikos Episkopoulos, were the 2 main AI engineers who developed the tool. And one important takeaway, as you also saw in this example, and one of the factors that contributed to this being a good tool is that although not a geothermal scientist, Kelly was thinking like one by the end of the project. And this is how she was able to provide you these examples and put herself in the place of a geothermal scientist using the tool. So now some technical discussion going back to the machine learning side. We basically have 2 explainable dimensions, which I want to dive one by one. The first is that the chosen model is explainable by itself. And what I mean is that we specifically choose a decision tree for this tool. And decision trees are models where the data traverse a series of nodes, seen here in the image, and then the data undergoes splits based on specific feature conditions, if then else condition, until they reach a final prediction or terminal node. And this splitting actually creates clusters value, and it's basically works like all regression models or models that predict values, but the decision tree have this additional capability of telling you where their prediction is based on. And you saw that in the tool also. There was a lot of information, so maybe it was not clear. The tool gives you the data point based on which the model based the prediction. So it will tell you that it is 170, and that 170 is based on the average between 160 and 180. So you can really control which data influence your decision. And that's a model that is explainable by itself in a way, because it gives you the why. Another layer of explainability, as also mentioned earlier, is the Shapley value. So we coupled this model with Shapley value. And what is Shapley value? There is a lot of theory behind Shapley value, but in a nutshell, it's a statistical tool that is borrowed from game theory. It treats the feature as player in a cooperative game, and the model output, so the prediction is the payoff, and then it credits each feature how much it increases or decreases the payoff. So how much it pushes up or down the average prediction. And basically, the feature credit is the marginal contribution of the feature when it joins the coalition of all the other features. And this is calculated independently of the order in which the feature are added. So one can also read this Shapley value from information theory, how much information is added. But that's the general idea. And practically, in order to use it, of course, you don't need to know all this. You can just look at the two plots that the tool has. The first one is the beesworm plots, where you see every feature overall contribution to the model prediction. So, for example, what does this plot tell you? You can see potassium, the first one, is the most influential feature for lithium prediction. And why is that? You can see the red points that are in high have high Shapley value. They increase the prediction very strongly. And then you have some other green points in the potassium to the left, and they tend to decrease the final prediction, but with smaller magnitude. So this gives you the overall, let's say, contribution of the feature to the model. And then the waterfall plots, which is the second feature that we added, is the same, but for a specific predicted lithium concentration. So as also seen in the video, you know that the tool gave you, for example, a prediction of what is the prediction here? Let me check. 0.32. And okay, how did we get this prediction? We started from the average, and we can see every input feature as moving this prediction left or right with plus or minus sign. And in the end, all the features are contributing, and you are able to see the contribution of each feature. That's the added value. So basically, as I said, there are two explainable dimensions, the model and the Shapley value, and these are further enhanced with maps and plots. And we're going to see now how this is done and why did we choose this this enhancement. So basically, let's go back. What we did is to have multiple answers to the question why we have this prediction. And why we have this prediction can be answered because this model took the average of this data point. That's the model explainability. And another answer to that question can be because each feature has contributed in this and this way. And that's the Shapley value answer to that question. And then we wanted to dig one step lower and have answer a sub-question. And for example, yes, let's go to the first answer. Why we have this prediction? Because the model took the average of this data point. Okay, that's fine. But where do these data point come from? And that's where you have the map. So you can really see where this data come from. So you have another way of assessing the credibility of your data, because as shown in the video, you might see that the prediction come from wells that are very different, and you might choose to ignore that or to take more into account. but in any case, you know where it comes from, which is a very important point in your prediction. And similarly, the other extra feature can be seen as an additional, let's say, layer to the Shapley value. So again, why we have this prediction? Because every feature contributed in this way. That's the Shapley value answer. Yes, but how are these features related to each other? And that answer is given by the plots that are shown here to the right, where we see each feature compared to each other. And so you can really go even deeper in these two explainable dimension by having these extra plots and maps built within the tool. Yes, so that was all from my side. As Catherine said in the beginning, please note all your questions, and we'll get back to those in the end. And now I'm going to hand over again to Kostas for talking about the commercial exploitation of the tool and potential next steps.
Thanks a lot, Stathis. Very well technical positioning and defending. Yeah, a few words about the future steps for INLECOM regarding this lithium exploration tool. The first commercial step in our strategy is to, and was, because this has also been something that's already been running, is to define the asset and position it in terms of market positioning and user interest and interest for actually sales. We all understand the global rising needs for lithium that Catherine very well introduced this in her slides a bit earlier. To estimate the lithium values, especially for old or even abandoned wells, is now is totally impossible, and these are something that we intend to focus. And of course, explainable AI, as Stathis very well highlighted, is something that opens a large door for further research on geochemical, geological conditions and process related to lithium exploration and lithium contents. For this, we have also started to identify target groups that could be geothermal energy developers, lithium exploration companies, directly actors that are extracting lithium or related technology providers, and of course specialized geological, hydrogeological consultancies, even research institutions and geological surveys, etc. Of course, this doesn't exclude future research, because that's something that needs to be further explored, further validated, further demonstrated, and also first from a technical standpoint, validating the technology in terms of capabilities and added value to the market, but also providing several other similar or not deployment options. This could include different materials, different extraction sites, different settings for these extractions, etc. That could, open some ways for the tool to expand, to scale, etc. in the market and better position itself. For this, we intend to have a quite wide push and pull, of course, approach regarding presence of the tool and how we're going to exploit and make some noise around it. Of course, leveraging the consortium network is something of priority with us. So that's why we are in very close contact with the consortium and its network. That's an immediate priority for the next 2 years, roughly. But also we will be, as Catherine said, quite active in large dissemination events and workshops for the next year at least. A good opportunity for us to present is the EC Raw Materials Week that is planned for November in Brussels. We plan to have a project presentation there. So if it happens that you are there, I will be myself presenting this tool and the project as well. So maybe we can have a more focused discussion. Of course, yeah, as I said before, further research and development for the next 3+ years is something that we are very much interesting to continue this research and these results, increase the TRL, increase the readiness level, but also the market readiness, and reach a point where we are very sure that this tool is marketable. There are customers that are willing to pay for it actually, and contribute also in the research and the geology domain in general. Next slide, please. That's it. So yeah, this is the link where you can find the tool. We intend after the workshop to share, of course, the recording of this video, but also share for you some links regarding which actually this link, but also some links to a questionnaire. So in case you have the opportunity to test it yourself, maybe you can provide feedback to us and let us know of comments, objections, reactions, or well done from your side regarding the tool, and we will very much appreciate that. Thanks so much from my side. Thanks to Catherine as the coordinator. Thanks to the European Federation of Geologists, of course, for the organization of the event. And thank you all for your participation. I think we have time for some questions.
Yeah, we will go over now to the questions. Thanks a lot, Kostas, for the presentations, and also Stasis for all the technical explanation. Really excellent. We have already some questions in the chat, and I invite all other participants of this webinar to also put your questions in the Q&A tool of the webinar. So we have the first question from Michael Dunne. Is it not true that lithium potential from geothermal fluids only is a small part of the lithium potential reserves when compared to brines and hard rock mining projects? What is the potential for lithium reserves in such projects? Yeah, maybe I can answer this myself.
Absolutely. Please do.
Well, I actually don't know exactly about the reserves or of lithium potential, but I can give you a few numbers of lithium that we find in the geothermal fluids. So the range of concentration of lithium in the fluids is between 10 milligrams per liter up to, let's say, 400 milligrams per liter in Europe. We have some regions with very high contents, around 180 milligrams per liter in the Upper Rhine Valley. Also in Cornwall, there are increased lithium values around 200 milligrams per liter. And also in the northern German basin, there are increased values, and there you can find up to these values of 400 milligrams per liter. And we have even seen single samples with 600 milligrams per liter. Now, 600 milligrams per liter still doesn't sound very much, but if you consider that in a geothermal power plant, you are pumping around 80 liters per second, then you can already see if you are not pumping only a second, but a minute and then an hour. And actually, those geothermal power plants are running around 8,000 hours per year. Then you come already to numbers that are quite high in lithium that you can extract from these fluids. And we've made preliminary calculations and seen that even a single well can contribute to around 0.5% of Europe's yearly lithium demand. So there is quite a potential in lithium from geothermal fluids. Whether it is higher than hard rock mining, I'm not daring to state that, but definitely it can make a contribution to the lithium supply in Europe. And the advantage is that it does not need such a big footprint. If you come to the Upper Rhine Valley and you say you want to have a lithium mine, a traditional mine there, I'm pretty sure that the social opposition would be quite high. And we have seen now already the first co-extraction projects in the Upper Rhine Valley, and I think the societal acceptance is quite well because it is essentially invisible mining, and that's where we think where the advantage of this technology is. Okay, then we have a second question from Karen Wagner-Weise. She is asking, considering the tool, whether the geology is considered in the tool.
Yes, so the tool, the geology is considered in the sense that it takes into account what the geologist would look for. So basically, we as data scientists took a long time of translating the geological problem into a data science problem. And once done for us, it's a tool that predicts lithium when you have available all the other values of all the other elements that are important for us, whether it would be the lithium that's predicted or boron or another element. It's exactly the same. We just switch variables. But so the geology part is considered in the sense of choosing the right variables that are interesting for geologists. And the geology is also considering the fact that we want to have a tool that is very easily readable from geologists, in the sense that it will help through visualizations and maps really help understand someone who is completely ignorant of data science to really understand why this prediction is there in multiple ways, whether that is the contribution of each element, whether that is with the data on which the prediction is based from, or whether that is where the data points come from geographically. So in that sense, geology is taken into account a lot during the design and the development of the tool. I don't know if this answers your question, but
yeah, maybe I can also add that at least in the second part of the tool, in this explainability part on the website, there, if you scroll down, you can actually choose whether you want to consider sedimentary basins, crystalline reservoirs, high enthalpy, or there was one more. So you can then choose whether you want to include all these different geological settings or geothermal settings, or whether you want to concentrate on just one of them.
Thank you, Catherine, for that clarification. Yeah.
Okay, we have one more question. Do you have empirical data on what is the minimum lithium content in geothermal solutions that is economically viable for extraction? Well, once more, I'm not sure whether one of you wants to answer.
Please go ahead.
Well, actually, I would say we don't have this data yet, at least in the project. It depends also very much on the extraction technology that you are using to get the critical raw material out, and the technologies that we are developing in the project are not yet at the level where it's really scaled up and you can really see the costs of the extraction. But definitely there are other projects and also commercial projects who have already made the calculation whether it's suitable for their reservoir and their lithium content, and have come to a positive conclusion. But I don't know the minimum lithium content and that would be suitable. I guess it depends also very much on whether you concentrate your development just on the lithium extraction, or whether you are really essentially first building up a geothermal power plant. You are actually making your business case with the heat extraction and then adding the lithium extraction on top. So I guess there are a lot of different business models in this combination of the two assets, heat and critical raw material. Okay, we have one more question. Is the depth of the wells from which these samples were taken integrated into the AI tool?
The depth by itself is not a feature that is, let's say, an input. So if you see the tool as an algorithm, is not an input. But as the depth is one data point that is in the data set, of course, one can link that this prediction was based on these data points, and this data point referred to that well, which is in that depth, and so on. So you can trace back to it, but it's not considered for prediction.
Yeah. Okay, thanks a lot. Do we have more questions from the audience? If not, I can ask a question myself in between. I guess you have answered it already a little bit, but could the tool also predict other elements except lithium?
Yes, absolutely, and it would actually be very easy for us. So for us, it's element agnostic, let's say. We just switch the column, read on, and you have another prediction based on other input features. So that would be amazingly easy to do. Yeah, absolutely.
I guess the only thing is that you need to have enough entries in the database
Yes, that's
to
right.
train the
That's
model
right.
with, right?
Yeah. So yes, let me rephrase. You might need to do some data search first in order to be sure that it works. But in theory, if the data are the same as lithium in terms of how many you have, very easy. Yeah.
Could the tool also use other machine learning techniques except the decision trees, for example, neural networks?
Yes, the tool could exactly as it is work with any other machine learning model that is used for regression or prediction, such as neural networks or anything else. The only problem is that if you do that, you will lose one of the dimensionality of explainability, which is, like I said, model specific. So you would lose the explainability from that decision tree gives you, which is knowing which data points are used for the prediction. But of course, one could do exactly the same with neural networks or any other model. Yes, absolutely.
Why did you actually choose for the decision trees?
The decision tree is one of the few machine learning techniques that tells you why the predicted value is such based on which data points the predicted value come from. So it tells you that my answer is 2, and I got 2 by averaging 1 and 3, and it shows you the 1 and the 3, the data points. So you can see the logic behind, let's say, its final answer. Whereas neural network will never do that. It will just give you the answer, and the way they've computed is by having all these black box internal layers of neurons that fire weights and so on, but you wouldn't know why.
Yeah. And I guess this is one of the big strengths from this tool, that it also in the long term could help us to really find out a bit what are the reasons for lithium content in a certain area, and what the contributions or the complexity of the processes are.
Yes,
So,
absolutely. And actually, I invite everyone who is listening to go in the tool and have a go, and don't hesitate to contact us and me personally if you have some difficulty using it or you want some suggestion. I'd be really happy to help, because for us it will really be added value if many people use it, and if we to give insight for people interested in understanding more in geothermal science. And I do think that in science in general, steps forwards are often made by joining forces between different fields. So this is such a case, and I invite anyone who is a little bit hesitant of using it to just do it and ping me, and I'll be happy to help him out if he needs anything.
yes, thanks. Yeah, I agree that it has been a great adventure working together with you and bringing together these two spheres from AI and geochemistry.
Yes,
But it also has been very beneficial to all of us. Yeah, I can only repeat Stacey's invitation to go to the tool and try it. You have the QR code here. You can just scan it and try it out. Have a look at what INLECOM has done. And as Costas already said, we will also share afterwards with you the link to the feedback questionnaire to really get your input on how we could still improve the tool. Are there any other questions? Last chance if you want to put your question into the Q&A tool. Well, I just wait another second, but well, if not, then I thank you very much for presenting the tool, presenting its advantages and the way forward with exploitation. And I thank everyone online for listening and asking the questions. As I said, we will have the next webinar on 23rd October on social license to operate on the guidelines developed, and then also Costas will present the tool once more during the Raw Materials Week. So if you want to get into direct contact, we invite you to join us in the Raw Materials Week. Yeah, and with that, yeah, I wish you a very nice afternoon. We are more or less perfectly on time. And I hope to see you soon in one of the next events. Thanks a lot. Bye-bye.
Thank you very
so
much.
Take care. Bye-bye.
Bye-bye.